In this briefing, we're going to talk about the 4 key variables that affect the weather, and we will also look at what we mean by dry adiabatic lapse rate, saturated adiabatic lapse rate, and environmental lapse rates. And I'm hoping that this will give you a really good grounding for the remainder of the MET course. This session itself will focus on a typical exam question, so that might give you a bit of a head start. The 4 important variables we're going to be talking about are air pressure, air temperature, air density, and the moisture content. And the top 3 are all completely independent. You change one and you change the other. And the moisture in the air, the moisture content, is a function of where the air has actually come from, what its the recent history is.
Clouds. We see them every day in the skies over our heads, but did you know you can make your own in your own home in a bottle? You just need 3 things: some water, the bottle, and some matches. First things first, you need to put the water in the bottle. Now, you can pretty much use any kind of plastic bottle, but with one this size, we found it worked best if it was around about 3/4 full. Put the lid on and give it a little bit of a shake. This allows the air in the top to become saturated in water vapor. Now, give it a squeeze. You're raising the pressure at the top of the bottle and the temperature. Let it go, and you're reducing the pressure and the temperature, but nothing is happening. Well, this is why we need the matches. Strike a match and pop it in the water. It soon goes out. You can't see any smoke particles in there, but now put the lid back on and give it a squeeze. As soon as you release, you'll see your cloud forming in the top of the bottle. So what's going on here? Well, initially, not very much. Not until we added the match, because the match adds tiny smoke particles, and you need those tiny particles, condensation nuclei, for the water droplets to form. You can't see the water vapor in the air initially, but give the bottle a squeeze, and it raises the pressure and the temperature. Let it go. The pressure drops. That allows the water to cool and condense, and it will form those tiny droplets, but only if you've got those condensation nuclei in there added by the smoke. They form tiny water vapor droplets, and that is the clouds that we see every day over our heads.
So first of all, let's talk about some very simple rules that you need to remember to help you get to grips with MET. The sun heats the ground, and in turn the ground heats the air, or indeed it cools it. It's not a case of the sun heating the air directly. Air is rather like oil. It doesn't mix very well. So one mass of air adjacent to another mass of air will take quite some time before it becomes sufficiently mixed to be able to be called one mass. Rising air, because it's going into an area of lower pressure, rising air expands, and because it's expanding, it cools. This is the adiabatic process. And conversely, descending air, as it's going into areas of higher pressure, it compresses and therefore it warms. Now, let's take a look at our bronze exam question. And that is, the surface temperature is 20 degrees C. The environmental lapse rate is 2 degrees C per 1,000 feet. The trigger temperature is 24 degrees. The dry adiabatic lapse rate is 3 degrees C per 1,000 feet. And the question is, how high will the thermals go? And initially, this question might look rather daunting. But I'll go through it step by step so you can understand how we go about answering the question. So first of all, environmental lapse rate. What on earth is that? And it's an expression that's used which is particularly misleading, because from the title you would imagine that the environmental lapse rate was some sort of fixed figure. And to make matters even worse, we have very often you'll hear quoted the environmental lapse rate at 2 degrees C per 1,000 feet, as per this question. And that comes from, that 2 degrees C per 1,000 feet, comes from the international standard atmosphere at 1.98 degrees C per 1,000 feet, so pretty damn close to 2 degrees. In truth, it's not a constant value at all, and we have never, in the history of aviation, in the history of weather, going back thousands of years, we've never had a situation where the temperature steadily decreases at 2 degrees C per 1,000 feet. It doesn't actually happen in reality. However, it is a very useful model to help explain what's going on within the weather, and we're going to be using it in our example now. So the surface temperature 20 degrees C, that's clear enough. The environmental lapse rate is, in this example, 2 degrees C per 1,000 feet, but in reality could be just about anything. The trigger temperature is the next point, and that's 24 degrees C. Now, trigger temperature is not something to be frightened of again. Trigger in my day was the name of Roy Rogers' horse, and it's got nothing to do with Roy Rogers' horse either. It is this, the trigger temperature is simply the temperature that an air mass at the surface has to be heated, and so it becomes sufficiently buoyant to rise as a thermal, and that's it. So, and that in itself is and can be a bit of a variable feast. However, for the purposes of our question, you've been given a value of 24 degrees. It then goes on to say that the dry adiabatic lapse rate is 3 degrees C per 1,000 feet. And what on earth is that? Well, adiabatic lapse rates, again, is another expression which is initially difficult to quite understand. If we take a parcel of air and move it up through the atmosphere, if you can imagine it a little bit like a balloon perhaps going up, then as the pressure as we go up reduces, so the parcel of air expands. So you can picture a balloon going up, and as it goes up it expands because the pressure around it is lower. Because it expands, it cools, and this is called adiabatic, because we haven't added or taken any heat out by any other means than by expansion or compression, in this case expansion, so no external heating. And this rate is a known physical constant, and it's either the dry adiabatic lapse rate, and that's a known physical constant, or it is the saturated adiabatic lapse rate. So once the air in the parcel of air is completely saturated, there's a heat exchange goes on and it rises at a different rate, which we'll have a look at in a minute. So this adiabatic lapse rate simply tells us how the temperature of the air changes with as we go up, changes with pressure. So now let's try and draw our exam question out. And you can see on the left hand side of this picture we've got heights rising up from the surface 1,000 feet, 2,000 feet, all the way up to 7,000 feet. And the surface is the horizontal line at the bottom. Now, looking at the temperatures, the surface temperature, which is now there, is 20 degrees C per 1,000 feet. And we know the environmental lapse rate is 2 degrees C per 1,000 feet. So as we go up through the atmosphere, you can see that the temperature is steadily decreasing by 2 degrees per 1,000 feet. And so, for instance, here at 5,000 feet, the temperature would be 10 degrees C. Now we move on to the next part, and that is the sun heats the ground, and in turn the ground heats the air. So here we have the sun heating the ground, and it heats the ground sufficiently for the air adjacent to it to be warm to 24 degrees. So it's 4 degrees warmer than its surroundings. And because it's now warmer and therefore more buoyant than its surroundings, it will rise. And as it rises, it will expand and it will cool. But it will cool at the dry adiabatic lapse rate. So here you can see at 1,000 feet it's 21 degrees. And at 2,000 feet it's 18 degrees. And you can see that the difference in temperature between the parcel of air and its surroundings is now only 2 degrees. As the parcel rises, it gets to 3,000 feet and 15 degrees, and then at 4,000 feet, the parcel of air is the same temperature as its surroundings. So bar a little bit of inertia, we can expect that thermal bubble to stop going up. And that's because the two temperatures are the same, and therefore the answer to the question is the top of the thermals are 4,000 feet. So actually quite a straightforward question if you just understood what all the words meant. Now what I'd like to do is move on from here and talk about what happens if we look at the dew point, because that hasn't been mentioned here. Now the air always has some water in it, always. Now the question is it saturated? So therefore can you see cloud, or is it not saturated? How much water in it depends on its recent history. So water is absorbed into the air by evaporation mainly. So so you can imagine if you take air and then pass it over the sea, it's got plenty of opportunity to gain water, and therefore it probably will. Warm air is capable of holding more water or more moisture than cool air. So if we take warm air across an ocean, it's going to absorb more water on average than if we pass cool air over the same ocean. And that accounts now for some part of the syllabus where we talk about air masses. And you can see here we've got tropical, maritime and polar continental and so on and so forth, air masses, which you will have picked up in your books. And what you need to understand when you're looking at this chart is it's dead simple. Polar air is cold, Arctic air is cold, tropical air is warm. Maritime means it came over the sea, and continental means it came over the land. So polar continental is a cool air mass that has been passed over mainly over land, and because of that it hasn't got much opportunity to absorb moisture. And it's really that simple. Getting rid of water in the air is typically done by precipitation. So that's rain to you and me, so or snow or whatever. So air absorbs moisture by evaporation and discharges it again by precipitation. So basically a cycle of water continuously operating. Now if we come back to our question, if I were to assume that the air at the surface in our example had a dew point of 10 degrees, what that would mean is if you could take that air, that particular parcel of air, and cool it to 10 degrees, it would saturate. But as you can see from the diagram, that's not going to happen because the air only gets cooled to 12 degrees. So it hasn't reached its dew point, and then therefore it hasn't saturated. So in these circumstances, no cloud is formed, and the day in gliding terms, we call that a blue day, no clouds. And this would account for why there aren't any on these days. So on blue days, the thermals can still be there, of course, if the other conditions are right, but there may be no clouds to guide the glider pilot. Now, if we try again, but this time we're going to put another air mass beside it with a different dew point. And this time the dew point is going to be 15 degrees C. Okay, now the same set of rules apply. The sun will heat the ground, and the ground in turn will heat the air. And you can see that the air warms to 24 degrees and breaks away from the surface, rises at the dry adiabatic lapse rate, so it's 21 degrees at 1,000 foot, 18 degrees at 2,000 feet, and 15 degrees at 3,000 feet. But of course 15 degrees was our dew point temperature. And then therefore, in this example now I've given you, this is where cloud base would be, and this is where cloud would start forming. Now something else happens. Because the air is saturated, it's now going to rise and cool, but at a different rate. And for the purposes of this example, I'm using 1.5 degrees C per 1,000 feet. It's not quite right. It's nearer 1.65, but 1.65 is difficult for the maths. So we'll keep it simple and we'll use 1.5, and you'll still get the point. So as this parcel of air continues to rise, when it gets to 4,000 feet, it's now 13.5 degrees. And when it gets to 5,000 feet, it's 12 degrees. And if you notice, the temperature difference between the parcel of air here at 5,000 feet and its surroundings is now 2 degrees. And as the parcel rises, continuing to cool at the saturated adiabatic lapse rate, it reaches 10.5 degrees and 9 degrees and so on. And you can see a continuing change in an increase in the temperature difference as we go up. And in these circumstances, you would have a towering cumulus, a big cumulus, which could be the basis for a big thunderstorm. The air mass above 4,000 feet is now unstable, and that is defined because the difference in temperature between our parcel of air and its surroundings is increasing, and all we did was added water. So there are 4 variables that we need to understand when we're trying to get to grips with the weather. So rather than try and memorize what the different things are, cold fronts, warm fronts, and so on, let's come back a step and look at it in terms of the pressure of the air, the volume of it, the temperature of it, and the amount of water in it. And if you can just understand those 4 simple but deliciously complex characteristics of the air, then you can start to explain anything you want to explain about the weather. So let's just look at some examples, and the first one here is a lenticular cloud. So wave clouds are, to the observer on the ground, something that appears to be stationary even though it's windy. It's a lens-like, so it's smooth-shaped. And what's happening is on the windward side, the air is rising, and on the downwind side, it's descending. The rising air on the windward side expands because it's going into an area of lower pressure. As it expands, it cools, and if it cools sufficiently, cloud forms, and that's exactly what's happening in these diagrams here. The air then, a little while later, starts to descend again, and as it descends, it compresses and it warms, and eventually the moisture there that was visible is reabsorbed into the air and the cloud disappears. And so what's happening here is the cloud is forming on the windward edge and decaying on the downwind edge. Take a look at another form of cloud here, orographic cloud, and we can explain it through the same basic principles. In this case, orographic cloud, the air has been forced up. It's mechanically lifted up because the wind, if you like, can't go through the hill. It's got to go up and over it. And because the air is forced up, it expands in the lower pressure higher up and cools. If the conditions are right, then it reaches its dew point and clouds form. If the difference between the Mendip Hills, for instance, which are about 2/3 of a 1,000-foot arc, then if the difference in between the actual temperature and the dew point temperature of the air at the surface, at the base of the hill, is 2 degrees or less, then cloud will definitely form on the hill. So it's very, very predictable. Another form of condition here, a Fern Wind, which is a good old exam favourite, and the same basic ideas. The air is forced up the hill. As it goes up the hill, it expands and cools at the dry adiabatic lapse rate. So it cools at 3 degrees C per 1,000 feet. At some point, it may reach its dew point, and if that happens, cloud forms, and that's basically an orographic cloud. As the air continues rising, it cools now at the saturated adiabatic lapse rate, and the water droplets within the cloud are getting larger and larger, and until in the end they can't be held in suspension anymore, and we get rain. So now, if that condition happens and we get rain, then the air is being dried out. Remember the water cycle, the rain itself is taking away moisture from the air, and it's changing the dew point. So as air descends down the lee side of the hill, you will find that it warms initially at the saturated adiabatic lapse rate, but it won't be very long because it's got a new dew point now where the remaining moisture will be reabsorbed into the air, and then it will continue its journey on down to the bottom of the hill, warming at 3 degrees C per 1,000 feet. And the net effect of all of that is the air coming in at the base of that hill is cooler than the air coming out at the base on the downwind side, simply because the air spent longer warming at 3 degrees C per 1,000 feet. And this is a very common feature. So if you go to places like the Canary Islands, very often you can see the prevailing wind side of the island is lush green, plenty of green foliage and so on, because it gets lots of water. And on the downwind side, it can very often be dry and arid. So quite a contrast from one side of these islands to the other. Places like New Zealand, South Island in New Zealand is another really good example, where they collect so much rainwater from the Southern Alps that they use it to generate electricity. So big tunnels dug through, and the rainwater is funneled past turbines to create electricity. And on the windward side of so in the case of New Zealand, the western side, you've got very large, broad-leafed, almost tropical plants, and on the downwind side it's semi-arid, it's almost desert. And in the UK, of course, we've got places like Wales, so the prevailing winds are typically westerly, so the moist air arriving on the Welsh hills is pushed up, and we get the Fern effect. So air rises up the Welsh mountains, it rains, that dries the air out, and the air on the lee side of the Welsh mountains then carries on across the country, but the air mass has been dried out, so it's warmer and drier, and therefore further inland you will find that the cloud bases have gone up. Now let's take a look at something like a cold front. Now again, what we have is a mass of cooler air catching up a mass of warmer air. And words are so important in Met here, because cold front might infer the air is cold, and that's only a relative term. So what we have, in fact, is cooler air. So you can have a cold front in the tropics, the same as you could have a warm front in the Arctic. It's a question of the relative temperatures, not the absolute temperatures. Now what happens as the mass of cooler air catches up with the warmer air in front is it pushes underneath it, and as the warmer air in front is pushed upwards. And because it's going up, it expands and cools, and when it reaches its dew point, it forms cloud. And very often on these frontal systems, that's enough to trigger the towering cumulus at times. Moving on to things like dew. Well, the sun heats the ground and the ground heats the air. We've already discovered that. And at night, the earth is no longer got the benefit of the sun warming it, and the excess heat in the earth's surface itself is radiated off at night. Now, assuming it's a clear night, because clouds will tend to behave like a blanket, assuming a clear night, then this heat is radiated off into space, and the surface of the earth gets cooler. And because the surface of the earth is cooler, it cools the air immediately adjacent to it. And this air immediately adjacent to it, if it's cooled sufficiently, reaches its dew point. And that's how you get dew. Radiation fog is another example. The surface gets cold by radiation, typically at night, and then in the early hours of the morning, when the surface is cooled sufficiently, that's cooled the air adjacent to it, which is then saturated. And because we have a light, very gentle wind, somewhere between 3 and 5 knots typically, then that air is stirred up and the lower air is replaced by upper air above it, and slowly but surely the fog gets thicker and thicker. And you will have seen this, if you're perhaps driving early in the morning, you can see the first wisps of fog, and then as your journey progresses, so you watch that fog actually getting thicker. Then the race is on. Will the sun come up to warm the ground, to disperse the fog, before the fog gets so thick that the fog itself acts as a barrier and reflects the sun's heating away from the surface of the earth? So quite an interesting puzzle. Okay, and that's the end. Thank you very much for watching, and I'll see you next time.